Hello, this is Lab 1, Constant Velocity, Jose Solis Ocampo. Introduction. The purpose of this experiment was to see if an object moving with constant velocity, meaning that there's zero acceleration, zero net force, and no direction changing, and see how it compares to its motion with a predictable computational model. So these are some of the fundamental principles we needed to know. First, what it meant to have a constant velocity, which was that the object had no acceleration and a zero net force since F equals ma. And Newton's first law states that object at rest stays at rest and object in motion stays in constant motion unless an external force is applied. And Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So kind of more force is needed with a greater mass for greater acceleration. Here's some of the equations I used for the experiment. Average velocity formula to help keep up with what our average velocity was. Our velocity update formula, and since we had previously seen that F net was 0, since our acceleration was 0, our final velocity and our initial velocity were the same, meaning that our experiment had a constant velocity. Position update formula to keep up with our position in our predictable computational model, and Newton's second law to just all around show that since we assumed a acceleration of 0, that the net forces were also 0. Here's a brief tracker's results. Since the line was straight, this meant that there was a constant velocity, and constant velocity means that there is 0 acceleration. That with the F equals ma equation shows that F net equals 0 and there's 0 net force. To get the average velocity, I did final position minus initial position over time, which is right here in meters, and the average velocity was 0.293 meters per second. Here's an experiment overview of our water bottle, which was our system, and the surroundings were air resistance, friction from the floor, gravity, and the initial push given. We used tracker to get our real world experiment and see the velocity and everything, and glow script for the computational model. Here are some of the initial conditions. We had at t equals 0. Well, first of all, we had applied all the initial position and velocity were all measured at t equals 0, which meant that at t equals 0, the initial position in the x direction was 0.146 meters, and the model assumed a net force of 0, resulting in 0 acceleration and constant velocity throughout the motion. And for my experiment, the total time was 2.8 seconds. Here's some glow script code that was given in tracker for the delta t, and this was the total time, 2.8 seconds of our experiment. And since we had previously seen that the F net was 0, I put this to 0 in the glow script. And here is where I added the momentum principle of Newton's second law in order to correctly update the position and velocity. And down here, you can see that the position update formula was used. Here's the glow script results. Here's the initial position, and here's the final position, and here's the motion of the water bottle given, which was accurate with the real world presentation. And the graph also shows that there is a constant velocity, meaning that there is a 0 acceleration and that it's very close to the real world and what we were looking for. So this is our comparison. The tracker line is in blue, the computation is in red, and this close agreement between the two suggests that the model accurately represented the physical behavior of the system, and we were correct to assume that the assumption of negligible net forces was reasonable. And here we can see that the tracker was just a little bit off, and that may be due to some errors. And some sources of errors were maybe I did the incorrect initial positions or velocity values. I didn't calculate friction forces or any other forces that weren't obvious, and I might have had some issues in computational models, including clicking wrong on the tracker portion. And finally, what if and what does it mean? So first, what if we flip the axis and the axis of our tracker? Well, this would mean that the positions and velocities would have opposite signs, and the graph would have a negative slope instead of a positive slope for the velocity and positions. And although it does have opposite signs, this still means that the magnitude of the velocity is the same, since it still went the same speed and traveled the same amount of distance. And since there was changing the axis does not change the forces. So all forces are unknown. So how do we know that F net is 0? Well, the forces are unknown, but some cancel each other out, and the summation of some opposite forces equals 0 or close to 0, and objects moving at constant velocity, which we saw with the computational model. And for the conclusion, Newton's first and second law were consistent with the findings. Actual results were extremely similar to expected results. And since the bottle had near constant velocity, we determined acceleration was 0, and F net says F net is 0. Thank you.